Hello everyone. In this video we are going to talk about SolidWorks nonlinear simulations. As you know, when you go to static simulations, the first thing that SolidWorks try to assume is that the material's behavior is linear. And by linear it means, like, for example, if the forces are doubled in magnitude, then the displacements are also doubled in magnitude, right? Or if you look at the stress-strain curve of the material, then the material is working in the linear region, right here, from basically zero load to the load that corresponds to what we call the yield strength. That region is linear and it's also elastic. One thing I want you to distinguish between is elastic and linear. They are not always necessarily the same. Okay, so the material could be linear but not or non-linear but still be elastic. So although here both linear and elastic are basically the same thing, because linear means, again, the relation between force and displacement, stress and strain is line, correct? It's a polynomial of first order. Elastic means if you let the force go, the path that the object or the force and the displacement on the curve travels is back to zero strain, zero force, or zero stress, zero strain. So if I come up from here and increase my force until I get to this point, so I travel this path basically. If at this point I let the force go, so bring the stress to zero because there is no force, there is no stress, also the strain or the displacement goes back, so I can go back from here all the way back to zero stress, zero strain, and have basically what we call no permanent deformation. That is called elastic. Right? Now for a material like this with curve like this, that's behavior elastic happens only in the linear region. Once you pass the linear region into what we call the plastic region, or the elastic region past the plastic region, you come here. Now if you pass the yield string and the material has yielded, now if I let the force go, you know that it goes back on a line parallel to the linear region, and it goes here because there is no force, there is no stress, but now there is this much of permanent strain or permanent deformation. So the material will permanently deform, but it doesn't mean that's necessarily the case for each material. There are some material that, as I said, they are nonlinear, so the behavior between the stress and the strain is not following a line, yet they are still elastic. Like, for example, the hyperelastic material like rubber, if you look at them, by the way, I think this should be Y instead of I. So if you look at the stress-strain relation for a hyperelastic material like rubber, the relation barely looks ever any linear. Mostly, if you look at it, it's entirely nonlinear. But if I start from zero stress, zero strain, and go up the curve, and I come here, right? So I follow this path, and I end up here. Now, if I let go of the force, the stress has to go back. So I should definitely end up on the epsilon line, but where? And as long as it is elastic, it's not going to go back parallel to any linear region because there is barely any linear region here. What it travels is something like this and still goes back to origin. And you see, the material at the end of the day has no permanent deformation. So the material is still elastic. Although what? Clearly nonlinear, because look at the relation between the stress and the strain. Okay, and the cycle that is formed, right, there is this phenomenon, we call it the hysteresis, if I have spelled it correctly. And hysteresis is basically an indication that there are intermolecular frictions, right, viscosity and so on, that is wasting your energy. So when you basically load and unload this material, you will lose some energy, right? So this is the hysteresis loop or cycle or whatever you want to call it. So that's the first thing I wanted to mention before I get into SolidWorks, that elasticity and linearity are two different things. Now, as I said, when you go to static analysis in SolidWorks, it is using a linear assumption, and it also assumes that the displacements are small because it assumes that the material that you are dealing with is a linear material that is elastic. And so when you are working in the linear region, the displacement or the maximum strain that you can have, this is just a small number. Because once you get into the plastic region, now your strain or deformation can be large. So we assume here that the material is working in such region and the behavior is following small displacement assumption. And this can be violated in many loading conditions for different types of material and so on. And that's where this nonlinear analysis can be helpful. In general, there are four types of simulation where the nonlinear analysis is needed. One, the material has to work outside the linear region. The material has a linear region, but because of the load being so big, it will pass the yield strength and end in the plastic region. Or the material is hyperelastic, so it barely has any linear region at all. Okay, and when the load goes up, because of this small slope, actually you can have very, very large displacements, very, very large strains. So for such material that can be deformed and basically stretched significantly, definitely you need to go with the nonlinear analysis. Linear analysis result is not going to be any accurate. Many times, even SolidWorks, I'll show you, like this case here, it will fail to even perform the analysis. The two other cases that you want to use nonlinear analysis is when the contact between the applied forces, right, and the surfaces, basically the contact surfaces, they do change versus time, the amount of contact. Like, for example, if you have this snap fit connectors or threads, if you look, when you have this snap fit connectors, when the part that is going to be snapped in, the fixed component comes in and deflects and then snaps in, if you look at the amount of contact that you have during this operation, you see that the amount of contact and the location of the contact does change. And so definitely that is not a linear behavior. Or if you have threads, right, if you have a bolt and a knot, right, let's say here, if I do just show you the section view. So like this is the section view of a knot, and then here you have this bolt that is fastened inside the knot, correct? Then if the loads are not perfectly symmetric about the axis of the bolt or not, definitely what you will see is this contact between the threads, the internal and external threads, will change over time. So sometimes you have some contact more here, sometimes a little bit more here, right? And the amount of surface contact does not stay constant as long as this load that is, let's say, applied to the knot or the bolt is not perfectly like vertical. If it's a little bit at angle, right, that makes the behavior different. Or when this bolt is being basically turned into the knot or out of the knot, also the location of the contact does change a little bit, and the surface contact is not going to always stay perfectly the same area. So for those analysis, it is always good to use nonlinear behavior and nonlinear simulation. And finally, if the direction of the applied loads or forces changes, so not just the contact, the direction of them. So let's say here you have a beam, a cantilevered beam like this that is fixed into the wall, and you are going to basically apply some loading to it and look at the bending behavior. When, well, this beam bends, so you go from the top figure to the bottom figure, what's going to happen if the load is attached to the beam? Then instead of having this direction, now it is going to have this direction, because it is going to be like a local normal, right? And so now you see the angle of the beam does change, and so now it is going to have also a horizontal component. It's not going to be just perfectly vertical anymore. And so now the behavior of that horizontal component, the effect of that on the rest of the beam has to be considered. So for such cases, again, it is better to use nonlinear analysis. So now let me show you in SolidWorks. So here we go to SolidWorks. Here I have a thin dog bone. And to take advantage of simplicity of this problem, I'm going to convert it into a shell or 2D. So right click, say shell. I convert it into a shell here, and I give it 2 mil thickness, the same as the original part, right? And then I set up the offset so it matches the geometry of the dog bone, the original 3D shape. And now I can create a mesh and show you. We have done this in one of my previous videos. So this is my mesh. Now I'm going to apply some fixed geometry on this edge here, right? If you remember, since the shell only has edge, not the surface, you are going to apply it over there. And then what I need is to apply some load here on this other side. So I go ahead and apply some force. I apply it here, and then along a selected direction, which is basically this direction. And then I'm going to give it some magnitude of 200 Newton in the reverse direction. And I'm going to study the behavior of this object here. So let's go ahead and run. It is made of aluminum 1060. And right off the bat, you see here, it says, hey, there are big displacements in this part, and you better consider large displacement. The small displacement assumption is not going to work. So do you want me to change it? Right now, I just say cancel. Don't do anything. Let me show you that, and then I'll show you the large assumption. So here, if you go to the static analysis, right click and go to properties, you see that here the large assumption is not checked, okay? So what it does when that error comes up, it turns on this large displacement and say, hey, assume that you can go with large displacement and now run. That's basically checking yes, and that does. But guess what? Even when you do it, still cannot do its job, okay? Because shell surface offset with large displacement is not even supported is in this static simulation in SolidWorks. So still it is going to fail even though you turn on the large displacement. In such case, what you need to do, you right click on this static and say copy steady, and then move it to a nonlinear steady, and then go there and now run the analysis here. It will definitely take a lot more computations and a lot more time for SolidWorks to perform the dynamic analysis. So here I fast forwarded a little bit for you. You see, after about 1 minute and like 50 seconds or 2 minutes or so, we are still at 1/3 of the analysis. The other thing here that I want to show you is if you look at the level of stress on the part, you see that the yield strength here is 2.7 times 10 to the 7, right? Pascal. But if you look at the max stress in the part, it already surpassed it big time. It's 7.1 times 10 to the 8. So it is about like 25 to 30 times more than the yield strength. And if you also look at the background on how big this dog bone is being bent, that is definitely a very large displacement. The good thing about it is I can pause it and then save the data until this very time point that I have. So as you can see, it's finally after some good time, several minutes, finally could do the analysis for me. You definitely see the big level of stress in the part and the huge amount of displacement. So if I right click here and just animate displacement at the scale of 1 to 1, you see that this is a very, very large displacement, and this is not something that static analysis in SolidWorks can handle. You definitely, for such behavior, need to go to nonlinear analysis. And there are more, as I said, scenarios here. So I just showed you one case of this. For the other cases, please also use nonlinear analysis. And what you can do is, as I showed you, just copy your static analysis into a nonlinear, so you don't need to redefine your forces, your boundary conditions, or anything, or even your mesh. But you allow the FEA method to take advantage of the nonlinear capabilities, and using a little bit more memory and a little bit more resources of your computational power of CPU, it can definitely, with a little patience, can give you some results that are more reasonable. Sometimes, let me warn you, this last thing and then we finish the video, is sometimes the static analysis might do something, might not just say, hey, I failed. Sometimes when you turn on the large displacement, the static analysis will actually give you some results. But if you look at the level of stress in it, or more importantly, if you look at the way that the part deforms, it does not really show proper deformations the way that you expected it to see. One of the cases that I saw on one of the videos on YouTube was it was like a hose ring that was supposed to go one full round 360 around itself, and when the educator turned on the large displacement, he could get it to perform FEA analysis, but when he showed the deformation, instead of going normal 360, it kind of had a crazy behavior. So let me just tell you. So it was this like long narrow parts, and then the goal of him was to round this all the way here and make it like a circle, right? This was the goal of basically turning around and completely wrapping that hose clip around the hose, right? So the behavior that you see, this side he had it fixed, and this side he gave it some rotation to have it full wrapping around the hose. But what happened is when he did turn on the large displacement, the solver did not fail, but when he ran the displacement animation, instead of this going the way that we expected, like this, it kind of went up like this, right? And then this part that was moving passed through the middle of the other one. So first it came to something like this, and then it became something like this. So a part of this material was basically passing through another part, which is, as I said, it's impossible for the material to do. So it was clearly a failure that was happening, right? The direction of the formation was wrong. The way that the material is cutting through itself was wrong. And it shows that although the failure did not happen in the static, but the results were wrong. But when he turned on the nonlinear analysis, now it did what it was supposed to do. So this will first turn on into something like this, and then further, and then further, and then finally the full round. Okay, so it did its job the way it was supposed to do. So if you see such huge displacements that I mentioned for you, right, going from this to this is a large displacement. That is definitely not something that you want to do with the static analysis. And even though you turn on the large displacement, it is still a nonlinear behavior. It definitely goes into nonlinear behavior and into the nonlinear region. So when you say large displacement, it doesn't necessarily mean nonlinear. It means instead of this stress strain being, for example, because the material was aluminum, so the behavior was kind of supposed to be something like this, right? So when you say large displacement, means, hey, turn down the slope of the linear region and make it something like this, correct? So still, instead of this much, I can have this much of displacement, but still assume that I'm operating in the linear region. But when you say nonlinear, means, hey, you do not need to do anything, just assume that the part is working in this area. Okay, so it's always prudent to jump right onto the nonlinear behavior when you see such big displacement and the material is working outside the elastic linear region for itself. So hopefully this video was useful to you, and I will see you in my next video.